Hey everyone, solving Advent of Code 2025, day 7 today. Uh, looks like a grid problem today, maybe. Um, cool. So, we get this. Let me paste it in. Cool. So, the tachyon beam enters the manifold at the position S, and it always moves downwards. If it encounters a splitter, it continues from the immediate left and immediate right. I see. So essentially, we kind of convert the current column into the sides, and then we proceed with it. The beam splitting, so it's split a total of 21 times. How many times will the beam split? I think we can think of this as kind of a row-wise sort of operation. So you'll see here that the first operation here splits once, and then after it splits once, it has two beams. These two beams split another time. So it would be 1 plus 2, and then there are 3 beams now, and with the 3 beams, those get split into 4. So it's 1 plus 2 plus 3 plus whatever this amount is, and it keeps repeating. Yeah, I think it could be some sort of math sort of solution, but because it's a bit simpler if we just solve it regularly first, I think maybe we can just do it as a regular solution. So maybe let me just increase the size of my window, and we can say rho is equals to the list of the given line, right? Cool. And then, so we need to know the tachyon row and tachyon column, right? And then maybe let's just store the splitters as well, which is the set of RC coordinates. Cool. Yep. And then what we want to do now is we can say R equals to 0 for C and the cell in the enumerate of a given line. If the cell happens to be S, the TRTC is equals to R and C. Otherwise, if the cell happens to be equal to this, we can say that we can add R and C. Otherwise, it's just a regular grid. Cool. And then, yeah, and then we can say that the columns is equals to the length of this line, and then the rows can increment by 1. Yeah, and so what we're interested in is the TRTC. So this is the tachyon. We're interested in the splitters, we're interested in the rows and the columns, because those define the boundary of my solution. Cool. So I have a tuple called a set of the RC coordinates, a int and an int. So we can say that the TRTC, the splitters, rows, and the columns is equal to the data. Let me just print this out. Okay, cool. And then we can start simulating this problem. So let's start by thinking of what a solution could look like, and I'm thinking we kind of process it row-wise, where for each row we figure out what are the beams that are in that particular row, and then we basically check if the following cell is a splitter, then we split it instead. Otherwise, we just include the next. Next position. So let's just call this the frontier. Because there is a chance we overlap, I'm thinking we should have the frontier be a set of the RC coordinates instead of being an array. And we can say while the frontier is valid, there is a new frontier, which is also a set. RC coordinates. So for every R and C, which is the current beam of light, so the current set should be with the TRTC. Yeah, and then let's have splits as the answer. So for every TRTC in the frontier that is given, the next position is equals to the row and then stay with the same column. If NR less than rows or not NC less than columns, it means that we have exceeded already. We can continue. And at the very end, we want to say that the frontier is equals to the new frontier. We can return the splits. Okay. If NR and C happens to be in the splitters, right, it means now we have to go to the direct right and direct left. So we can say LR, LC, which is the left version of this, is equals to the NR C minus 1. And the RR, RC, which is the right of this, is the NRC plus 1. If so I guess we could say for DC in minus 1 and 1, we can say that the KRKC, let's just say the KRKC is the NR and the NC plus DC. If not, so if it happens to be split, we can increase the answer, but we know that the beam of light that isn't within the range we want to basically discard. Otherwise, as long as it's within the range, KRKC. Otherwise, if it is not in, we can simply add NR and C. Yeah. Cool. So that is a bit off. I wonder why. Let us try printing out all of these answers first. So let me print out the frontier each and every time. Cool. So we reached this. We discovered that 2 and 7 is a splitter. Oh, sorry, or not. Cool, yeah, so we discovered it split 42 times. Yeah, and you can kind of see here. I see, so the splits only count as one, right? Because you hit encounter one splitter. Cool. Wow, it's a really nice input. Day7.txt 1553. Yep. Cool. So it's only a single particle. So the I see. Yeah, so we're interested in the number of ways it could go. i.e. The paths that it could have taken. And I guess what we could do is, as a second part, so the first part is sort of a, not really a BFS, but sort of a BFS solution where we go through each row and we figure out if you could have kind of contributed to it. The alternative I can think of is, if I'm interested in this explicit number of paths that I have taken, what I would do is I would DFS instead. So let me just write up what it might look like. So you have DFS, you have the RNC. If it is not, right? And so the DFS at each point should always return the number of paths taken to that given point. I think like there is a sort of multiplicative attribute where for each sort of splitter we take into account of, we know how many possible paths there are. I actually do think it is possible for us to do it this way, because I think essentially the way we can see it here is, okay, maybe let me just hide this first, but display the test on this, and let's print out the frontier. Yeah, you can kind of see here that it is sort of looking at, okay, so there's one path, and then suddenly there's two paths, three paths. So I'm assuming there is some sort of mathematical property we could have exploited here, but I can't really think of how we can generify it, so maybe let's not be overly ambitious for now. Cool. So let's just say that the ways is equals to 0. Let's return the ways. Okay. Cool. So let's just return the DFS where TRTC is the very start. So one thing we want to do is we can say if R is if R plus 1C happens to be in the splitters, then ways has to increment by the ways it goes to the left and to the right. Yeah, and then essentially this lets me know the paths that it has taken throughout this grid. So yeah, and then let's see. Well, we want to check if R has reached the rows, which means I've reached the very end. Let's return 1, because you have successfully reached the very end. Oh, why is this the case? Oh, sorry. Otherwise, if it is not in the splitters, it's just the DFS of R plus 1C, because you stay in the same column. So I guess you don't really need ways. You could just kind of do a return of this plus this, right? Yeah, cool. So this one is a bit inefficient because now it spans across many columns and rows. So I think we can actually use the func tools. We can import the cache, and let's annotate this with the cache. Yeah, so this would be the solution we get. Cool. Yeah, I guess I guess if we really wanted to solve the first as a kind of sort of DP DFS problem, we can do something similar, where rather than returning the number, we can literally just return. We can do something like, if it is in splitter, we would do return 1 plus DFS of plus 1, C minus 1 plus DFS of row plus 1, C plus 1 plus 1. Otherwise, we simply return this because we don't actually know what it is. Let me check again if that's the right answer. I don't think that's the right answer. It is not. Yeah, I'm trying to think. Well, basically the idea here is, as long as I've encountered a splitter, the sort of global answer would have increased. So I guess we could do splits is equals to 0. We could do non-local splits. This could return none. But we could do DFS, and then we can say the splits can increase by 1. Otherwise, we can do something like this. Oops, turn the splits. Yeah, so it's 1553 was the same as the previous one as well. So I guess that's like an even simpler solution as well. I think today's, again, surprisingly really simple. The fundamental idea here is we just treat it as a graph, and each and every time we kind of draw the beam, either we count the number of times we see a number that is in the splitter, or the alternative is the by kind of going through all of the possible paths, we return it. And because this is a sort of a DP problem, we can just check if we have seen this before. I think there are like some potential ways we can optimize a little bit. So I think one of the main things we can notice is we always kind of only care about the maximum number of beams or maximum number of paths taken from the previous path plus any additional paths that come afterwards. So if we do want to change this to be a sort of a bottom up approach, it would be slightly different. We can just keep track of just the previous row and the current row and just operate based off of that. But yeah, I think today is relatively straightforward actually. I was expecting something even more difficult because the past few days were a bit softer. But I guess it's good practice just to figure out how these algorithms work as well. Cool. Alright, thank you guys. See you tomorrow.